solving systems of equations algebraically by elimination, which sometimes some people refer to this as the addition or subtraction method, right? And so one of the questions that you have to ask yourself when you go to solve a system is, do I want to solve this graphically? Maybe it will solve very nicely graphically, easy to do. You get an exact answer. Life is good. Or maybe I just don't like solving graphically because I can never draw them properly, and if I have software, maybe that's good. Or I need an exact value, and the software is not going to give me that, so I need to solve algebraically. Then one of the questions you ask yourself when you're solving algebraically is, do I do it by substitution or elimination? So the criteria for substitution is what? What is the criteria for substitution? Yes, and?
First we have to solve for one variables and then plug that value into the.
So how does that work, Trevin?
A variable one essence coefficient?
Yeah, so a variable that has a coefficient of 1, right? So you're looking at these two equations and you see, x plus 3y equals 7. You go, oh, I can solve this by elimination, by substitution, right? Because I can solve for x. When you don't want to solve by substitution is when you see something like this. Or not, because it's not writing. 3x minus 5y equals negative 9, and 4x plus 5y equals 23. Yes?
Well, in that case, we have to add the equations together.
Yes. Yes. So the elimination method, also called addition or subtraction, is, hey, look, if we add these two equations together, we're going to get a different equation, right? I mean, first of all, that's the thing. It's going to be a different equation. If we graph it, it's going to be a whole new line, but it's going to go through the point of intersection of the original two lines, okay? So anything we do by modification, by way of modifying a system, if I multiply a system by the same number, we just get the same line, right? We know that, right? Those are they're not parallel lines, they're the same line, right? They have infinitely many solutions, same slope, same y-intercept, right? If you reduce them to slope-intercept form. So if we add these two equations together, or we subtract one equation from the other, we will get yet another equation, right? But it will pass through the same point of intersection, okay? So why don't we take a look at that? We'll just go, let's go to Desmos, and we'll just graph those two. So what was the first equation? 3x minus 5y equals negative 9?
Yeah.
Okay. And what's the second equation?
4x plus 5y.
Okay. Oh, sorry. Okay, spoiler alert, we're actually going to end up solving this, right? As soon as we graph it, we're going to see where the point of intersection is, right? But we're still going to do this algebraically. So apparently they intersect at 2, 3. Right? Kind of obvious. This would be nice by graphing, right? Because it's a nice, obvious point of intersection. Okay, if we add these two equations together, what are we going to get? So 7x equals positive 14, right? Hit enter. And it just says x equals 2. It's not really a line, I guess, or it's not going to graph the line x equals 2. So maybe, can I just hit that and then it'll graph that? Nope. Can I go back? Nope. Can I get rid of that keyboard? Yeah. Go back. Go back. Wow. Now I get a keyboard. And all right, what were the equations again? 3x plus 2y equals negative 9. And, 5y minus 5y plus 5y. 3x plus 5y equals negative 9. And what was the other one? What? 3x minus 5y?
No, it's 4x.
3x minus 5y equals negative 9. And what was the other one?
4x plus 5y equals 23.
Okay, and then we had x equals 2. If I just, okay. So if I don't type it in as 7x equals 14, but just reduce it, x equals 2. Different line, but what does it do? Right? Passes through the same point of intersection. What if we subtract one equation from the other? What would we get? Negative x minus 10y equals minus 32. Goes through the same, different line, but where's it going? Through the same point of intersection, right? What if we take a multiple of one of these lines? So let's multiply this by 2, right? What's that? 6x, oops. 6x, oh, disappeared. Let's do the other one then. 8x plus 10y equals 46. Okay, which is actually just this, it's the same line, right? So you're not seeing, but where's the new line? Well, it's just on top of one of the original ones. Okay, so you can take multiples of a line, you can add two lines together, you can subtract two lines, or sorry, two equations. You can add two equations, you can take multiples of an equation, you can add two equations together, you can subtract it, and the nice thing is, goes through the same point of intersection, right? So we're allowed to add or subtract, right? So that's so what we're going to do is we're going to do elimination by adding, because what will that do? It will eliminate the y. Okay, so let's call this 1. Call this 2. Okay, and we're going to go 1 minus 2. 3x minus 4x is negative x. Oh, sorry, we're adding, right? We're doing 1 plus 2. 3x plus 4x is 7x equals 14. The next line that follows is obviously x equals 2. Okay, now at this point, remember yesterday I said once you've solved for one of the variables, then both methods become the same. We are then going to substitute 2 for x in which one? 2. Doesn't really matter, but 2. Yeah, why not 2, right? That way there's no negative to deal with, right? We're just going to get an 8 and move that over, and 15, and it's 3, and we already knew it was 3 because we already saw it graphically, but you know, let's be surprised. Anyways.
Oh my god.
Okay, so what we're doing is, just make a note over here, if you like, so we're going to add, if we add these equations, adding these equations, will eliminate the y variable. Okay, thus solving for x. And once we solve for x, then we're going to substitute. So now we're going to substitute 2 for x in equation 2. Right? Wouldn't matter if you put it into 1, same thing, right? You get the same solution. There's only one answer for it. So 4x plus 5y equals 23. 4 times 2 plus 5y equals 23. 5y equals 15. Y equals 3. The solution is the ordered pair. And let's just keep them in alphabetical order, right? So if you're doing A's and B's, then it'll be A comma B. If you're doing Q's and K's, then it'll be K comma Q. Go with that. Most time it's just X's and Y's, right? Because why do we use X as the unknown?
Because Spanish doesn't have a sh sound.
Because there's no sh sound in Spanish. Right? If you want to see a cool, although maybe somewhat outdated series, there's a series that was on BBC called Connections with a guy named James Burke, who would do this kind of thing, right? The exact same thing. It's like, why do we use X as the unknown? Well, because there's no sound in Spanish, right? And he's got this, there's Connections 1 and Connections 2. You can probably find it online somewhere. Maybe it's on YouTube and that. But it's sort of like, you know, why is something the way it is today? Well, because 1,000 years ago, this happened, right? And literally, it is. It's because 1,000 years ago, this one particular event happened, and that's why, you know, why are the space shuttle rocket boosters the width of 2 horses behind? Okay, now I don't know if this is true, but the explanation goes like this. in ancient days, right, when Rome was in charge of Britain, or they had invaded Britain, and you have these horse-drawn carriages, carts or carriages, right, and usually pulled by 2 horses or 4 horses, like chuck wagons, 2 in front of the other. Then the carts were built to a certain width, and the wheels were a certain width. They created ruts in the road, and you pretty much had to stay in those, right? I mean, it's like driving in the snow. Well, you guys probably don't drive too much, but when you get to driving here, side streets will often get rutted. You just stay in there. It's easier, right? Because most car widths. But anyways, so when they started to build, so that became a common distance apart. So when they started making railroads, they kept that distance apart. And when they made railroad tunnels, then maybe they made them so that the trains would fit through. And when they made rocket boosters here and had to ship them by train there, they had to make them so they fit through the tunnels, which were just wider than the rails, which were set at the same width as the cart wheels, which were the set width of 2 horses behind, because that's how the carts, right? So theoretically that's true. I don't remember if James Burke's ever mentioned that, and maybe it isn't true because of that, but it's sort of that idea, right, of, something happened 1,500 years ago or 1,000 years ago, which has a ripple effect, right? So the series is called Connections by James Burke. Okay, so if we want to check this, we're just going to take 2, 3. So 3 times 2 is 6, minus 15. 6 minus 15 is negative 9, right? I'm not doing any formal checks here. 4 times 2 is 8, plus 15 is 23. Always go back to here, because if you messed up here, you will have then solved a different system, not the original system, and it'll be wrong. And I'll know it's wrong, and you should know it's wrong. So when I mark the test, it's like, yeah, you handed this in 10 minutes early. You should have known this was wrong, because you could have checked it in the original system, right? So your responsibility is go back and check in the original system. Whether we say to or not, right, doesn't matter. Now, if you run out of time, that's fine. I mean, you can't check. And don't check, if you want to run a quick mental check, 6 minus 9, yeah, okay, okay. Then that's fine. Don't spend a lot of time checking these, not on a test, right? Then you run out of time, and it's, I ran out of time. Well, sorry. Not my fault. Okay. What if? Well, let's do one where maybe we subtract. So 4x plus 3y equals 5. And 4x minus 7y equals 15. 1, 2. What do we do? Well, if we add, we get 8x and negative 4y, which, well, it passes through the same point, doesn't actually help us to solve, right? We want to eliminate a variable. So we could multiply either equation by negative 1, right? We know that won't change anything. I mean, it'll actually take the line and do that to it, but it'll still go through the same point, okay? We never did that. Let's go back here. So what if I do negative 8x minus 10y equals negative 46? That actually just be the exact same one. Never mind. Forget what I was saying. Okay. So what are we're going to subtract, right? So we're going to do 1 minus 2. 1 minus 2. 4x minus 4x, 0. 3 minus negative 7, positive 10y. Bless you. 5 minus 15. Negative 10, y is equal to, substitute negative 1 for y in, why not 2? It'll make it positive. Well, I guess. Doesn't matter. Substitute negative y, negative 1, sorry, for y in, okay, heads 1, tails 2.
Tails. Other side.
Polar bear.
Damn.
Okay, that's 2. For y in 2. 4x minus 7y equals 15. 4x minus 7 times negative 1 equals 15. 4x plus 7 equals 15. 4x equals 8. X equals 2. Solution, 2, negative 1. Yep.
So you go back to the original 2, right?
Yes, the original 2. Always to the original, because when you multiplied, which we haven't done yet, but if you have to modify one of those two, if you make a mistake doing it, you will be solving a different system. You'll get a solution. It'll be wrong. And so we go back to the original, right? So we think it's 2, 1. So 8 minus 3 is 5. And 8 plus 7 is 15. Works, right? Both. Got to work in both, right? Otherwise, if it satisfies one, it just says it's on the one line, but maybe it's on the other. Maybe it isn't on the other line. All right, let's step it up a notch. So, what if? Let's go for the hard. Well, not the hard. Hardy hard. 3x plus 2y equals 2. And 4x plus 5y equals 12. Okay, call that 1, call that 2. Now, be aware, maybe these are written as 3x plus 2y minus 2 equals 0, and the other one's written as 4x plus 5y equals 12. So you want to make them look the same, right? In other words, usually when we solve by elimination, we have the x, the y, equals, and then the number. Okay? Just usually makes it easier to solve. Doesn't really matter, you could have x, y number equals 0, right? But generally speaking, if you have the x, the y, and the number over here on the other side of the equal sign, because you're going to eliminate one variable, ending up with something times x or something times y equals number, quick divide, done. Okay, so usually it's like this. Okay, we got a problem. I can neither add nor subtract these and get rid of a variable. So what are we going to do? Yes, I can either add or subtract these, but it won't eliminate one of the variables. So why bother? We could create 75 different new equations, all passing through the same point, yet none getting us any closer to a solution.
Multiply by the
Lowest
lowest common denominator.
common denominator is 1.
Or possibly, or multiple.
All right, what's the idea? We need to make the coefficient of
X or Y.
x or y the same. Let's write this down. We need to of either x or y the same. X or y the same. Or same coefficient, opposite signs, right? If you like to add, so everything's positive here, right? So, you know, if I say multiply this by 4 and this by 3 to make the x's both 12, or multiply this by 5 and this by 2 to make the y's both 10, then I would solve by subtracting. If I multiply this by 4 and this by -3, then I can add. So your choice, right? Dealer's choice. You get to pick the game. You just have to solve by elimination. If you don't mind subtracting, and in this case it's not really a big deal because you're just subtracting a positive number from a positive number, right? The only time you get into trouble, really, and even then you shouldn't, you're subtracting negatives, you got to remember to add, right? But so x or y the same, or the same value, but with opposite signs. Okay, heads x, tails y.
Polar bear. Polar bear.
Yeah, polar bear again.
Oh, called it.
This is weird.
Well, here, we'll do it this way.
Polar bear.
Wait, I can do this.
That's magic. Polar bear.
Yeah. I forget. What do we say? So tails was number 2, right? No, tails was y. Right, we're going to make the y the same. Okay, so here's what we're going to do. I can do more impressive. Watch, I can do it with $5. Okay, now, do you want to go with both plus or 1 plus 1 minus? All right, heads both plus, tails 1 of each. What are the odds we had 3 tails in a row? 50-50, really.
Polar bear.
Heads this time. All right, so what was heads? Both the same or one? I think it was everything positive, right? Okay, so here's what we're going to do. We're going to go 5 times 1. Right, that's 15x plus 10y equals 10. Most common mistake, you don't multiply the right side. Right? You do this and this, you leave that as a 2. Most common mistake. You guys aren't very common, right? You're uncommon, so you won't make that mistake. You'll come up with something entirely different, I'm sure. You're going to go 2 times 2. Right, something where I just put question marks and go, I honestly have no idea what you're doing here. 8x plus 10y equals 22, 4. 24. Okay? So what do we have the same now? What are we going to eliminate? How? Yeah, we're going to subtract, right? Okay, so what do we get? Now, if you want, we could call this 3, this 4, and then over here we're going to say we're going to do 3 minus 4. Yeah, I don't know if you need to do that or not. It's nice to do the 5 times 1, 2 times 2, right? Because you're showing what you're doing. Like I'm multiplying this by 5, I'm getting my y's the same. All right, so we get 7x equals, and x equals. And at this point, whether we are solving by substitution or elimination, it's all the same, right? We just substitute into 3 or 4, into 1 or 2. Okay, heads 1, tails 2. I would just leave the coin out. Right? It's like the coin toss for the Grey Cup. But it's indoors, so it doesn't really matter. You know, so
On the roof!
There's no wind.
Not sure what
Head or bear?
There's an upside down head. So yeah, heads. All right, heads 1. So we're going to go back to number 1, right? Which is 3x plus 2y equals 2. So we're going to substitute. Negative 2, 4x in number 1, right? Go back to the original. If you made a mistake in multiplying, again, you will have created a new system. Because you'll have your original 2 lines, you'll have a third line which is not one of those, and it'll intersect with one of your original 2, right? And then you have this new system that you've solved, which is not going to get you a lot of marks. Okay, what was 1? 3x plus 2y equals 2. 3x plus 2y equals 2. 3 times negative 2 plus 2y equals 2. 2y equals 8. Y equals 4. Negative 2, 4. Okay? Let's run a quick check on that. Where? 3 and 4? 5 maybe? 1 and 2. What did I say it was? Negative 2 and 4. Negative 6 plus 8 is 2. Negative 8 plus 20 is 12. Yes. Right? 2 thumbs up. 1 for each equation. Okay? You got 2 thumbs up. Next. I haw. We do 2 more examples. One example, we won't solve this. I'll just show it to you in case you run into something like it. So, let's say we got a couple of rational expressions over 3 equals 1. That's number 1. And we got x plus 3 over 2 plus y minus 3 over 4 equals 1.
Multiply everything by 12.
No.
Damn it.
Well, maybe. I don't know. That's thinking further ahead than I was thinking. So the first thing that I would be thinking is, okay, let's get rid of the denominators, so let's multiply by Grant. What is it? Now it actually is applicable.
Lowest common denominator.
There you go, the lowest common denominator. So we like to eliminate fractions, right? And we can eliminate fractions by multiplying by the lowest common denominator. So we could multiply number 1 by 6. Now, if you have a little foresight, you'll say, well, I'm going to end up with a 3x and a 2 on the y, right? A 3 and a 2. And then I'm going to multiply number 2 by what? By 4. That'll give me a 2 on the x and a 1 on the y. So we had a 3 and a 2 and 1 and 2. So if we multiply number 2 by 8, then we could solve by elimination by getting the y values the same, right? That might be thinking a little bit too far ahead. So, you know, it's sometimes easier just to take baby steps than it is to take this big leap. You know, and I think it's probably easier really just to take the baby steps, right? You're just doing one thing at a time, just saying, all right, I'm going to get rid of that 2 and the 3. Okay, I'm going to multiply by 6. So we're going to go 6 times 1. Right, which is going to give me 3 times x minus 3 minus 2 times y minus 5 equals 6. Okay, which is going to give me, because this all has to be arranged, right? 3x minus 9 minus 2y plus 10 equals 6. It's going to give me 3x minus 2y plus 1, so subtract 1 equals 5. Right? New equation. What do they have in common? They're actually the same line. Right? A multiple of a line is just the same line. Okay? And we're going to multiply 2 by 4, or 4 by 2. Okay, so what's that going to give me? A 2 on the x plus 3, and nothing on the y minus 3. And most common mistake, people don't multiply the right-hand side by the number. Right? Because you kind of, you're so excited to get this right, and you sort of lose interest by the time you hit the equal sign, and you just equals 1. Yeah. So you got to actually pay attention. 2x plus 6 plus y minus 3 equals 4, or 2x plus y, that'll be plus 3, so we'll minus 3 equals 1. So how would you solve this? Substitution, obviously, right? Y equals 1 minus 2x, put that in here, boom, done. So you could do it by elimination, right? In which case, what would you do? You multiply this by 2, or negative 2.
1.5.
But 2 makes the most sense here, right? So if you are going to, and there's nothing wrong with doing elimination on something like this. Yes, it solves by substitution. The only time that it's wrong is when we say solve by substitution, and you don't. Because you get 0. Yeah, hey, you got the right answer. Great. I got the right answer if I graphed it. We didn't ask you to do that. We wanted to see if you could solve by substitution. We want to see if you can solve by elimination. Question?
I was going to ask, for like, that we just solved, can we...
We haven't solved anything.
I mean, sorry, we just got rid of the denominators?
Yes.
Can we still label that as 1 and 2?
No. 3 and 4.
But it's called a sheet equation.
Well, we
Never mind,
think
never mind.
it is.
Sorry.
Hopefully it is, but if we messed up, it isn't. So they really are, you know. Yes, if I graphed 2 and I graphed 4, you would only see one line. Okay? That is true. Because it's just a multiple. A multiple of a line is just the line. Okay? But I'm not going to solve it, right? But just showing you that if you have this situation, this is what you do. And this solve. These are really, they're trivial. That's even easier to solve because it's just. So let's pick one other one. Last one. 2x plus 3y equals 8. And 5x minus 4y equals negative 6. Okay, which variable shall we eliminate?
Flip a coin. Flip 2 coins.
All right. Flip a coin.
I saw me flip a coin there.
Oh, this time it's the loony.
Oh.
Okay.
The loon.
Heads X, tails Y.
Yes. Loon. Land on the side.
Heads.
Oh no!
Okay, let me leave this up. Okay, we're going to eliminate X. What do I have to multiply by to eliminate X?
That's why I like.
Okay, and we're going to go 2 times 2. Add or subtract? Subtract. What's 15 minus negative 8?
23.
What's that equal to?
52.
What's y equal to?
2.5.
You really got to work on your math. This goes a long way towards explaining marks. I'll tell you that. Now, we have a choice. We can substitute 52 over 23 into either 1 or 2, or we could say, why don't we just go eliminate the y? That way I don't have to deal with fractions, right? And not nice fractions either. It's not like the 2 goes into the 23. You know, if there was a 3 on the bottom of that and that was y, I'd stick it in number 1, the 3's would cancel. It's just going to be a nice number. This is not going to be a nice number, right? It's going to be an ugly fraction, and it's going to create more than. Then I got to change the 8 to being over 23s, right? Or I got to change the, you know. So instead, we'll do what I'm going to coin a double elimination, right? We'll eliminate the x, which we did, and then we will go through and we will eliminate the y. Okay, so what are you going to multiply by? Number 1.
4 times 3.
4 times 1. 8x plus 12y equals 32. What do we multiply 2 by? 3. Sorry, I'm not going to wait. 5x minus 12y equals negative 18. Add or subtract? Answer is yes. You can do one or the other, but we'll add. So 23x. Not terrifically surprising that the denominator is going to end up as 23, right? Because if you stuck that in there and there are no denominators, then it's likely you have to get 23rds. Also, 23 is prime, and therefore it's not going to reduce with anything, right? It's not like I got a denominator of 9 and get like 10 over 9 or something, then the other one might be over 3. So this isn't surprising. Equals what? 14. And so x is? Okay. So do I want to check this? Well, this is 28 23rds, and this is 156 23rds. 156 plus 28 is 184 23rds, which I'm willing to bet is 8. And then this is 70 23rds minus whatever 4 times 208 23rds, which is whatever negative 6 is times 23. If you want to check it on your calculator, you could graph both of those. You could solve it graphically, get a decimal, and then check and see if that decimal is 14 over 23. And then get a decimal for y and see if that's 52 over 23, right? That's the lazy way to check. You could just type it in your calculator, right? 2 times 14 over 23 plus 3 times 52 over 23, 8, wow. And then 5 times 14 over 23 minus 4 times 52 over 23, negative 6. Great, checks. Okay? Don't check till the end. Unless we say show a formal verification, then don't do it, right? Quick mental check, fine. This one, leave till the end, right? You don't want to be checking, you don't want to be spending time checking this until the end. You can come back, you got a bit of time, you can throw it in. You could also store 14 over 23 in A and 52 over 23 in B, right? And then just type 2A plus 3B, and then just type 5A minus 4B. Or if you type it in the first place, you can hit second function, enter, and go edit the 2 to be a 5, and go minus 4 instead of plus 3, and then hit enter. Right, so, yeah. You can do it in less time. All right, this concludes the formal part of the lesson.